Good day, ladies and gentlemen. Today's video is going to be a short little one on Snell's law, which handles the diffraction of light. Now, diffraction of light is the bending, quote unquote, of light. And the easiest way to describe this is if you look at a glass, or perspex usually, block. And if you have a ray of light moving into that block, you of course have your normal, which is the line at 90 degrees to the surface of the block in this case. Now, as you may remember from grade 10 work, I believe it is, different substances have different optical densities. The optical density influences how light moves through that object. You might have noticed if you put a straw into a glass of water, the straw almost looks like it bends. That's because the way light moves through the water and air is different. It's exactly the same thing happening here. The glass, or perspex block, is more dense. It has a higher refractive index than the air around it. So if this light ray were to continue straight, it would continue along that dotted line. However, that is not the case. Now, very simply, if something goes from a less dense to a more dense medium, then that light ray is going to bend towards the normal. Towards the normal. So this light ray is not going to continue along my dotted line. It is going to continue like that until it hits this surface, where we again have a normal. Let me just label them. And if it were to continue straight, it would continue along my dotted line. Now, when something moves from a more to a less dense medium, you have the opposite of this. So rather than bending towards the normal, it will bend away from the normal. So it would continue straight along there, it bends away, so it goes in that direction. Now, this is more or less the basics of diffraction, sort of a visual representation. Snell's law is a little bit more technical. Snell's law is how you actually go about calculating these angles. Now, the simplest way to explain this would be to sort of zoom in on one of these. Let's say we have the one side and the other side, and we have the optical medium 1 and we have the optical medium 2, or the refractive indices rather, because what the actual mediums that the light is moving through are actually irrelevant. The calculations for this uses the refractive indices. So we are simply going to call them N1 and N2 for the refractive index. Then of course we have our normal, and then we have our light ray. Now let us say that our light ray is coming in like this, and it ends up, it would have continued like that. It bends away from the normal, so it goes in that direction. You've realized by now, if you've watched previous videos, I'm not a terribly artistic individual, so I do apologize for the quality of my sketches, but please try to imagine it looks better. Now, the important part is that this angle right over here, we'll call that theta 1. That is the angle of incidence, the angle at which the light ray hits the boundary between the two different optical media. This angle over here, we'll call that theta 2. That is how much this ray of light is refracted, how much it is bent. Now, whether this light ray moves into a more or a less dense medium in terms of our calculations is utterly irrelevant, because provided that we put the right refractive index and the right theta angle in the right place in our formula, we will get the correct angle over here, irrespective of whether it's going from a less to a more dense medium or not. And the formula that we use for these is N1 sine theta 1 is equal to N2 sine theta 2. Now, this in and of itself doesn't particularly help a lot. So let's do a little example. I find that those are often the best way to explain these things. So let's say we have a ray of light, and this ray of light passes from water to air. So we have water over here. Here the ray of light goes, and it passes into air. Now, because we are reasonably intelligent individuals that can think for ourselves, we know that air is less dense than water. Not so. And remember, our rule was if it goes from less to more, it bends towards. But now we are going from a more dense medium to a less dense medium. So it will bend away from the normal. Not so. So it's going to go in that direction. Now, I can tell you that the refractive index, the N for water, let's call it N1, is equal to 1.33. The N for air is equal to 1.0001, I believe. So it is pretty much always rounded to just 1. And I tell you that the angle at which this light ray hits the boundary, our theta 1, is equal to 30 degrees. So my question then is, how much is this light ray refracted? In other words, what is this angle over here, which we will call theta 2? Now, like I said at the beginning, if a light ray goes from a less to a more dense medium, it bends towards the normal. We are going from a more to a less dense medium, so it's going to bend away from the normal. So already we can sort of figure out that this angle over here, our theta 2, is going to be bigger than theta 1. So if the answer you end up getting is smaller than 30 degrees, you have done something wrong. Okay? The reason I am taking time to explain this is because a lot of people just sort of do the formula, plug the stuff in, quickly get an answer, and then move on. Don't really bother to check. I apologize if you can hear the dogs barking. They don't really bother to check the answer. However, this basic knowledge and basic application of theory tells you already, before you've done anything, that your answer needs to be bigger than 30. So if your answer is smaller than 30, you need to check yourself. But moving on. Our formula, of course, is N1 sine theta 1 is equal to N2 sine theta 2. Now here is a trick, and this is a trick that I have noticed is not actually explained in textbooks. Now, obviously you plug your stuff into your formula. Our N1 for water is going to be 1.33 sine 30 degrees is equal to N2, which is 1, and then sine theta 2 which is what we want because we don't know how much is refracted. And now you can fiddle with this formula around and you can do everything. Obviously, anything times 1 is just that thing. So we are going to have 1.33 sine 30 being equal to sine theta 2. The fact that we are going into air and we have a 1 over here makes this a whole lot easier. Obviously, this is a linear equation with only one unknown, so you can move the whole thing around to get 1.33 sine 30 over 1 is equal to sine theta 2, but that's not necessary right now. You can do that if you want, and if you do choose to follow that path, I would advise you to swap your formula around over here, not after you've plugged stuff in. So for this example, you would then have n1 sine theta 1 over n2 is equal to sine theta 2. It works a lot better if you move your formula around before you start plugging stuff in. But anyway, now if I take my little scientific calculator over here, I don't know if you can actually make out what's happening on the screen. I'll try to angle it a little bit for you. And if you plug in 1.33 sine 30, that actually gives you 0.665. 0.665 is equal to sine theta 2. Now that is very obviously not the correct answer. I mean, to start with, we said your answer needs to be larger than 30. And this step is not explained in textbooks I found. Over here we have sine theta. We only want theta. So we have to get rid of that sine. The way we do that is, you might see on the calculator, right there above my sine, is a sine minus 1. So if I press my shift and then sine, you will see it pops up sine minus 1. If I then enter 0.665 in there and I hit equals to, it gives me 40.1 or 41.6, I apologize. So that gives us 41.68 degrees is equal to theta 2. Because remember, we want the theta only. We don't want sine theta. And textbooks really do not adequately explain how to do this step over here. So you need to use the sine minus 1 function on your calculator with the answer you get over there. And that is going to give you your answer. So the answer up here, 41 degrees. Now, this is something I would advise some practice in. Perhaps make yourself a little example, exactly the same as I've done here. Make up 2 refractive indices, anything you choose. In general, I would not advise you go above maybe 3 or 5, because the things that we encounter in everyday life do not have such dense refractive indices. And then pick an angle, any angle, and then try to calculate how much it is refracted. It's a nice little way to train yourself and to practice to get this in. Of course, you can also get a different way of this being asked, where they give you both of the angles and you have to calculate one of the refractive indices. It's exactly the same thing, linear equation, one unknown. Now, if that is something that you're interested in, you want to see me do a few examples of this, or you want to see me do an example where you calculate the refractive index rather than the angle of diffraction, you can drop a comment or something like that, and I will see about making a little video just for that for you guys. This was Snell's law and a little bit on diffraction of light. That's it, ladies and gentlemen. Until next time.